But first of all, a recap on position vectors, because we're going to be using vectors in projectile motion. So reminder, position vector. So here is our position vector, a vector that's anchored to the origin. Different ways we could write it. I could write it as use my position vector with a tilde underneath it. OP with the arrow notation. There it is. That is a position vector. I don't really like this notation, but yes, you could write it as a coordinate x, y. I personally steer away from that because I then get confused. Am I talking about the points or am I talking about the vector itself? Column vector I much prefer because then it's obvious I'm talking about the vector. And of course we could break it up into its two components. And traditionally we say the horizontal direction is the I direction and the vertical direction is the J direction. The magnitude of the vector, basically Pythagoras, square root of x squared plus y squared. And the direction of the vector is the angle it makes with the positive x-axis. So the inverse tan of y on x. Very similar to what we see in complex numbers, which makes sense because we look at complex numbers as vectors as well. So what is a space curve? So everything we've looked at so far, motion has been in a straight line, but clearly not everything moves in a straight line. We're going to think of our position vector. We tend to use r for some reason for position vector. It doesn't have to, of course, you can give it any pronumeral you like. It's some function of t, which probably is going to represent time in this situation. Here is that position vector. As a particle moves, so if the endpoint of this vector is basically the position of the particle, so as it moves it would create a new vector. So after some change in time I'm now over here at Q. But then I could move again and I'm now over here at R. A bit more time, I'm now over at R. If I had every single point of the path of the particle, I could come up with a curve that represents the path that it's travelling on. And that's what we call a space curve. Now, how do I find its velocity? Well, the velocity will always be the tangent at that particular point. You can sort of imagine the vector as a string, if you like. And if you were to cut the string, it would shoot off at a tangent. So at P, my tangent would be going in the direction of that green vector that I've drawn in. I'll call it V. Notice the tilde underneath, so it's telling me it's a vector. Don't get lazy and leave off those tildes. It's kind of important. We know it's a vector. Now, in a text, or so sometimes in tests or in textbooks, you might see it written as bold without a tilde. But of course, books can do that. It's very hard for you to do that when you're writing. So we put the tilde there. To find the velocity and the acceleration, then again, we could break it up into the components. But then by breaking it into the components, once again, I've reduced the problem to just straight line motion, and that's what we're used to seeing. So displacement, so we could break it up into its two vectors, and we would have an equation for displacement in the horizontal or the I direction. We would have an equation for the displacement in the Y direction. Velocity, then, we would just differentiate each of those components, and we'd come up with a velocity vector. And the magnitude of the velocity vector would be, well, the square root of x dot squared plus y dot squared, whatever those values are. The direction, inverse tan of y dot on x dot. So it's the velocities we're interested in. Acceleration, we would then differentiate the velocity components, and we get components for acceleration. Interestingly, you'll see I've only put direction on velocity, because whenever you're dealing with it, it's the velocity that controls the direction, because the velocity is how you're moving. That's what you look at if you want to work out direction. You look at the velocity vectors. So a particle is going to move, and here is the velocity vector broken up into its components. They've told us the initial velocity, so when t equals 0, is simply I. So it's moving horizontally with a magnitude of 1. Find the position vector at any time. Okay, let's break it into them. We just basically got two straight line motion problems to solve. In the x direction, we're saying, well, dx to t will be minus 2 sine 2t. I can separate out my variables. Initially, horizontally, when t equals 0, we said it was 1. And we want to find a link between t and x. So we get x is cos 2t. Now we just do the same thing for the y direction. So dy to t is 4 cos 2t. Separate them out. Now vertically, the initial velocity is 0. There was no j component in my velocity initial conditions there. So integrate that one, and we get y is 2 sine 2t. Essentially, we've just created parametric equations. But putting it together as a vector, there we are. Our displacement vector then would be cos 2t in the I direction, 2 sine 2t in the j direction. Position vectors, so we've got two different particles this time. We're going to prove that they collide when they're travelling at the same speed, but also at right angles to each other. If they collide, we know they occupy the same position at the same time. Right? They could occupy the same position at different times, but they're not going to collide. So it has to be the same position at the same time. I'm just equating on the left-hand side the x components, because that means their x components must be equal at that particular time, and I could work out when they collide. Mind you, cubic. Bit tricky. Maybe it's easier to look at the y's. Let's see what happens there. In the vertical direction, t squared is 3t. That's going to be easier to solve. That's a quadratic. So I might work on that one first of all. Solving that, I get two possibilities. Now, which one is it? When they collide, I can now go back to my first equation and see which one works, because it has to satisfy both of these components. If I sub in 1, I get -1, so it mustn't be when t is 1. Sub in 2, I get 0. Great. So they do collide. They're occupying the same position at the same time of t equals 2. So I do know that. They gave me the displacement vectors. Differentiate, I can get the velocity vectors. So there's the one for A. There's the one for B. So when t equals 2, subbing in the 2, we have our velocities at that particular point. We can work out the magnitude, because they wanted the speed. So 5, we've got that. And 5 over, yes, they are travelling at the same speed. They wanted to know that. They both come out to be 5. And the dot product, yep, that's 0. So yep, they're at right angles to each other as well. So we've found both things that they wanted us to find. Here's an interesting one from last year's HSC. It was actually a multiple choice question, and they drew this particular space curve. There it is. And which one is consistent, basically? And they're looking at the dot products of the different vectors. So there's the space curve. I said, well, all right, here's one particular point on there. Let's investigate. What do I know? Whilst I don't know the actual values, I do know that the x and the y component is going to be positive, because if you look at the coordinates, clearly we're in the first quadrant. I do know that for the r vector, that both of those will be positive. I know the velocity vector would be going off at a tangent. Now, if I was to break that into its components, the horizontal one's going to the right, so it's positive, and the vertical one's going up, so it's positive as well. So I do know that about the velocity vector. Again, I don't know the actual numbers, but I know it's got to be greater than or equal to 0. Yes, at the point I've drawn in, it's going to be positive, but because it could be anywhere on that space curve. If it was at the very starting point, the x velocity would be 0. So greater than or equal to 0, I know it's going to be that. So r dot v, whilst I can't work out the value, I can work out the sign, because I'm going to get a positive times a positive and a positive times a positive. For both of them, it's going to be a positive number. They also told me the particle is slowing down. Slowing down? Deceleration? Oh, that's when acceleration is in the opposite direction to velocity. And I have worked out the direction of velocity. I know the acceleration must be in the opposite direction. So they're both negative. So now I can investigate A dot V. I go to positive times a negative plus a positive times a negative. Well, that's going to be negative. Okay, so we match up our choices. I forget which one that was, A, B, C or D, but that's the one we would be looking for. R dot V is positive and A dot V is negative. So that's the idea that we're then going to use to look at projectile motion, and we'll do that this afternoon.